Welcome. Tonight there is nothing to solve, nothing to remember, nothing to do, but rest. Let your shoulders sink into whatever is holding you. Let your breath find its own unhurried rhythm. Tonight we drift through a quiet kind of factory, the one that manufactures time itself, gear by gear, crystal by crystal. You need only listen and let your eyes grow heavy whenever they wish. Brass is the primary alloy used for clock gears. It is a blend of copper and zinc, warm gold in color, chosen because it resists wear and turns smoothly against itself for decades. Inside almost every mechanical clock, tiny brass wheels mesh together in silence, each tooth shaped to carry motion forward without slipping. This same alloy has carried the hours since long before electricity existed. Deep within granite veins, quartz crystals grow across thousands of years, then are mined for use as oscillator components. Miners once pulled these clear stones from Brazilian hillsides by hand, searching for pieces flawless enough to vibrate with perfect regularity. Each crystal, cut and shaped correctly, becomes the steady heartbeat inside a modern watch. The stone that formed in darkness ends up keeping track of daylight. Silicon wafers, thin as paper and impossibly pure, now carry the timing circuits of chip-based clocks. Cut from cylinders of refined silicon, each wafer holds thousands of microscopic pathways etched with light. Inside these pathways, electrical pulses count time far faster than any gear could turn. What began as beach sand becomes, after enormous refinement, the quiet architecture beneath a digital clock face. Ruby jewels reduce friction in mechanical watch movements, easing the tiny pivots where gears must spin thousands of times each hour. These are often synthetic rubies, grown in laboratories, then polished into bearings smaller than a grain of rice. Without them, metal would grind against metal, and a watch would wear itself out within a few short years. A few red gems, hidden from view, quietly extend a lifetime. Steel mainsprings coil tightly inside a small barrel, storing the mechanical energy a clock needs to keep moving. When wound, the spring tightens like a held breath, and as it slowly releases, it pushes the entire mechanism forward. This coiled steel ribbon, sometimes stretched over a meter long when uncurled, can power a watch for a full day or more from a single winding. Stored tension becomes measured motion. Cesium metal, soft and silvery, lies at the center of every atomic clock resonator. It reacts so quickly with air that it must be sealed away, yet inside a vacuum chamber it becomes remarkably still, vibrating at a frequency so exact that it defines the modern second. Physicists at national laboratories rely on this element's steady pulse to measure time more precisely than any mechanical device ever could. A whisper. Thin layer of rhodium protects watch movement parts from corrosion, plated over brass and steel components through a careful electrochemical process. This coating, only a few micrometers thick, keeps moisture and tarnish from ever reaching the metal beneath. It also gives certain parts a bright, mirror-like sheen. Beneath that gleam lies decades of quiet defense against rust, unseen by anyone wearing the watch. Sapphire crystal glass covers the faces of premium watches, chosen for a hardness surpassed by very few natural materials. Grown synthetically at extreme heat, then cut and polished into flawless discs, this glass resists scratching for a lifetime of daily wear. Light passes through it almost untouched, letting every hand and marking beneath stay perfectly visible. What protects the hours also lets them be clearly seen. Gold appears in both decorative cases and delicate electrical contact components, valued for beauty above and reliability below the surface. On the outside, it is shaped into elegant casings that catch light and hold their color for generations. Inside certain movements, thin gold wires and contacts conduct electricity without corroding, a quiet dependability hidden beneath ornament. The same metal that adorns a wrist also keeps a circuit faithfully closed. Let your breath find its own slow measure now. no counting required. Each inhale arrives a little quieter than the last, each exhale a little longer, unwinding something you didn't know was wound. There is no rhythm to keep, only one to follow. Let it lengthen on its own, the way a tide pulls back further with each pass. Somewhere beneath the ribs, the whole body begins to settle into that same unhurried tempo. Lithium batteries send a steady trickle of power through quartz wristwatches, small silver discs no larger than a fingernail. Inside each one, lithium atoms release electrons in a controlled, patient current that can last for years without fading. This tiny cell asks nothing of the wearer beyond time itself, ticking on unnoticed in the dark of a drawer or the warmth of a sleeve. Its quiet charge is the hidden heartbeat behind every quartz hour. Beryllium-copper alloys form the fine springs found inside many modern watches, valued for a springiness that brass alone cannot hold. This blend resists fatigue even after millions of tiny flexes, bending and returning to shape without weakening over years. Engineers favor it for parts that must move constantly yet never fail. Coiled thin as thread, it carries tension the way a held breath carries patience, ready to release at exactly the right moment. Aluminum cases lighten the burden of industrial timers, shaving away ounces that steel would otherwise demand. Factories that once relied on heavy iron housings turned to this pale, workable metal for its strength without weight. A pocket-sized timer built from aluminum can be carried all day without notice, its casing cool to the touch and resistant to corrosion. Lightness, in this case, became its own kind of precision. Platinum finds its way into the movements of the finest chronometers, prized for a density that steadies the swing of a balance wheel. Watchmakers shape it into tiny weights and select components where mass matters more than shine. Heavier than gold, yet gentle on delicate pivots, platinum lets a movement hold its rhythm, even through small jolts of daily wear. Few wearers ever see it, tucked as it is beneath the dial's calm face. Nickel alloys shield certain clock parts from the pull of stray magnetic fields, a threat mechanical movements rarely escape in a world full of phones and speakers. These alloys resist becoming magnetized themselves, keeping steel gears and springs from clinging to one another in ways that would slow or stop a watch. Inside a case no bigger than a coin, this invisible resistance keeps time moving at its own honest pace. The Swiss Jura Mountains rose from quiet farmland into the historic heart of watchmaking, their long winters once leaving farmers with idle hands and patient hours. In small stone houses, tucked along the valleys, families began assembling tiny gears at kitchen tables, passing skills from parent to child across generations. Over centuries, entire villages grew around this craft, their identity woven into springs and hairsprings, as much as into soil and snow. Waltham Watch Company pioneered interchangeable parts manufacturing in the 1850s, transforming a craft once shaped entirely by individual hands. In its Massachusetts factory, machines cut identical gears and springs with a consistency no single artisan could match alone. A broken part in one watch could now be replaced by an identical piece from another, an idea as revolutionary then as it seems ordinary today. Precision, suddenly, could be repeated endlessly. The Industrial Revolution introduced assembly line methods to clock production, replacing solitary workshops with long rooms of coordinated motion. Where one craftsman once built an entire clock from start to finish, dozens now each handled a single repeated task, passing components down the line. Output multiplied far beyond what any individual hands could achieve. Clocks that once belonged only to the wealthy began appearing in ordinary homes across entire cities. Black Forest craftsmen shaped some of the earliest cuckoo clocks by hand, carving wood into birds, leaves, and tiny hinged doors over long winter months. Working by candlelight in wooden cottages, they whittled gears from local timber before metal parts became common, each clock a small forest scene brought indoors. These clocks traveled far beyond their German valleys, carrying a quiet folk artistry into homes across distant continents. Seiko began automating quartz watch production in Japan through the 1970s, building factories where machines handled steps once done entirely by hand. Circuit boards, tiny motors, and quartz oscillators moved together through synchronized assembly stations. Precision multiplied, and so did volume, as thousands of identical movements emerged from a single production run each day. A technology once confined to laboratories had found its way into ordinary wrists across the world. Feel the weight of your body now, settling deeper into the mattress beneath you. Notice your feet first, heavy and unmoving, then let that heaviness travel up through your ankles and calves. Your hips sink a little further with each breath. Your shoulders grow dense, as though something warm has been laid gently across them. Even your hands feel full, resting where they lie. There is nowhere this heaviness needs to go, and nothing asking it to lift again tonight. The quartz crisis nearly destroyed the Swiss mechanical watch industry during the 1970s and 80s. Cheaper, more accurate quartz movements from Japan flooded markets, once dominated by Swiss craftsmanship. Entire towns built around mechanical watchmaking watched factories close and generations of skill fall quiet. It took decades and a return to luxury and heritage marketing for Switzerland's watch industry to recover its footing. Big Ben's mechanism took shape inside a London workshop in 1859, built by clockmakers working with exacting tolerances for its era. Edward Dent's firm crafted the massive movement, whose pendulum and escapement had to survive wind, temperature swings, and decades of continuous use. Its accuracy became a point of national pride, regulated by adjusting old pennies stacked upon the pendulum itself. That modest trick still helps keep London's most famous clock steady today. The first factory-made pocket watches appeared across 19th-century America, produced by companies eager to bring precision to a wider public. Before this, pocket watches were largely handmade luxuries, assembled one at a time by skilled individuals. New machine tools allowed identical parts to be stamped and fitted at speed, lowering costs dramatically. For the first time, a farmer or a factory worker might carry the same kind of timepiece once reserved for the wealthy. Timex introduced mass-produced affordable watches in the years following World War II, applying wartime manufacturing techniques to civilian timekeeping. Their movements used simplified designs and durable pins instead of costly jewels, making repairs unnecessary at such low prices. Advertising promised toughness as much as accuracy, showing watches strapped to boat propellers or dropped from towers and still ticking. Suddenly, an accurate watch was something almost anyone could own. The Longines factory established standardized watch calibers during the 1860s, creating movement designs that could be produced consistently across many models. This standardization meant parts from one caliber could serve across an entire family of watches, simplifying both manufacturing and repair. Longines became known for balancing industrial efficiency with careful engineering, a reputation that carried the company through more than a century of continued production. Early tower clocks were built one at a time by individual master clockmakers, each mechanism shaped through years of trial and personal skill. These craftsmen forged their own gears, cut their own teeth by hand, and calculated escapements through experience rather than formula. A single tower clock might take a master and his apprentices months or years to complete, their names sometimes engraved quietly into the ironwork itself. The Meiji era brought Western clock manufacturing techniques into Japan during the latter half of the 1800s. Japanese workshops that once built traditional wadokai, clocks measuring uneven seasonal hours, began adopting European gear trains and standardized time. Engineers traveled abroad to study foreign factories, then returned to build Japan's own clock and watch industries. This shift laid early groundwork for the country's later rise in precision timekeeping. Elgin National Watch Company grew into America's largest watch factory by the late 19th century, its sprawling Illinois plant employing thousands of workers. Elgin produced millions of movements across decades, supplying railroads, soldiers, and everyday households with dependable timepieces. Its factory town became a community built almost entirely around the rhythm of watchmaking, with generations of families passing through its assembly halls. Soviet Russia built state-run watch factories, among them Polzhou in Moscow, established to supply timepieces to a vast, unified state. These factories operated outside market competition, guided instead by centralized production quotas. Workers assembled millions of mechanical movements over decades, often adapting designs drawn from earlier European calibers. Poljot watches traveled into space, worn by cosmonauts, carrying Soviet engineering far beyond the factory floor into orbit. China became the largest producer of wristwatches by volume during the 2000s, its factories in Guangdong and Fujian turning out hundreds of millions of movements each year. Vast assembly lines combined quartz components sourced globally with fast, coordinated labor. Entire towns grew around watch and component manufacturing, exporting timepieces to markets across the world. The center of mass production had shifted from Switzerland's mountains to China's coastal factory belt. Outside, past the walls, a faint hum rises and fades, arriving and receding like breath moving through a house settling for the night. It might be wind finding a loose shutter or a furnace ticking somewhere down the hall. You don't need to name it. Let it come close, then drift away again, and let your body sink a little further with each pass, arriving, receding, asking nothing of you at all. Escapements regulate the release of energy inside mechanical clocks, converting steady spring tension into measured, discrete ticks. Without one, a wound mainspring would unwind all at once, releasing its energy in a single uncontrolled burst. Instead, small toothed wheels catch and release in rhythmic increments, doling out power one pulse at a time. This mechanical negotiation between spring and gear is what gives a clock its steady, audible heartbeat. Gear trains multiply rotational speed between one component and the next, translating the slow turn of a mainspring into the fast sweep of a second's hand. Each wheel meshes with the next, its teeth cut to precise ratios. A single rotation at the barrel might become 60 rotations by the time motion reaches the escape wheel. Centuries of refinement went into calculating these ratios by hand, long before calculators existed. Balance wheels oscillate at a fixed frequency, swinging back and forth with a rhythm as steady as a metronome. Each swing releases one tooth of the escape wheel, translating motion directly into measured seconds. A typical balance wheel completes several beats every second, its tiny weighted rim swinging with almost hypnotic regularity. This small oscillating ring is, in essence, the true timekeeper hidden inside every mechanical watch. Hairsprings control the timing rate of a mechanical watch, coiling and uncoiling with each swing of the balance wheel. This delicate spiral of metal, thinner than a human hair in places, determines exactly how quickly the balance oscillates. Adjusting its length or tension changes a watch's speed by fractions of a second each day. Watchmakers once shaped these springs entirely by hand, coil by coil, under magnifying lenses. Pallet forks lock and release the escape wheel with each swing of the balance, acting as a tiny gatekeeper between stored energy and measured time. Two small jeweled pallets rock back and forth, catching one tooth, then letting it go. This brief mechanical handshake repeats many times each second inside a running watch. It is a small, endlessly patient exchange, one that continues unnoticed on countless wrists around the world. Barrel arbors house the coiled mainspring at the center of a watch's power system, holding tension that will unwind slowly over hours or days. The spring wraps many times around this small cylindrical core, tightly coiled after winding. As it releases, the barrel turns just slightly, feeding measured motion outward through the gear train. This single component quietly stores nearly all the energy a mechanical watch will ever use. Jewel bearings reduce wear at the pivots where friction runs highest, placing tiny polished stones wherever metal parts spin against each other. Rubies, often synthetic, cushion these points with a hardness that resists scratching for decades. A fine watch might contain more than 20 such jewels scattered through its movement. This small use of gemstones has nothing to do with decoration. It exists purely to help time run smoothly for years. Computer-controlled cutting tools now shape watch gears to tolerances measured in millionths of a meter. A Slzz machine traces the outline of a tiny gear again and again, removing metal in passes finer than a whisper of dust. Each tooth emerges with an edge so precise that thousands of copies can be made without a single flaw drifting in. Where a craftsman once spent hours filing a single wheel, a machine now finishes dozens before the light outside has fully changed. Stamping presses fall in steady rhythm, shaping raw brass into the plates that will become a watch movement. A flat sheet feeds forward, a die descends, and in an instant a rough outline of gears or bridges appears where blank metal once lay. The press repeats this motion thousands of times a day, each stroke identical to the last. What began as featureless brass leaves the press, already carrying the shape of the machine it will one day help keep alive. A small half-moon rotor swings freely inside an automatic watch, turning with every motion of the wearer's wrist. As it spins, it wins the mainspring little by little, gathering energy from something as ordinary as reaching for a cup or turning a doorknob. No battery, no manual winding, just the accumulated drift of an ordinary day converted into stored power. The watch, in this sense, is fed by the same hands that wear it. Let warmth begin somewhere small, maybe the center of your chest, and let it spread outward from there, unhurried, like a color slowly filling a page. Feel it move down through your arms, loosening your hands, easing your fingers open. Let it drift lower, through your stomach, your hips, down each leg, until your feet feel heavy and warm against the sheets. There is no need to rush this warmth. It has all night to travel through you. Laser light traces fine lines into brass bridges, etching serial numbers too small to read without magnification. The beam moves with a steadiness no hand could match, burning tiny characters into metal that will outlast the watch's owner. Each number is unique, a quiet fingerprint hidden beneath the dial where almost no one will ever look. It exists mostly for the watch itself, a record it carries, unseen, for its entire working life. Inside a clean room, filtered air moves in gentle currents, keeping dust away from movements being assembled by gloved hands. A single stray fiber or speck of grit could jam a gear train meant to run for decades. Workers wear caps, masks, and static-free suits, moving with the deliberate care of people handling something almost invisible. The room itself seems to hold its breath, filtered and still, so that tiny machines can be born without interference. Near the balance wheel sits a small regulator arm, ready to nudge a mechanical watch's rate faster or slower with the gentlest touch. Moving it a hair's width changes the effective length of the hairspring, and with it how quickly the watch ticks through each day. A watchmaker adjusts this arm, checks the rate, adjusts again, circling closer to perfect timing across many small corrections. It is fine, tuning measured not in seconds, but in fractions of a second, repeated patiently until the balance settles into rhythm. Shock-absorbing springs cradle the pivots of the balance wheel, cushioning them against sudden drops or bumps. Without this protection, a single knock could bend the delicate axle that lets the balance swing freely. Tiny spring-loaded jewels let the pivot shift slightly under impact, then spring back into precise alignment once the shock passes. This small system, hidden deep in the movement, is often the difference between a watch that survives a fall and one that stops forever. Pulling the crown outward disengages the keyless works, letting a watch be wound and set without any separate tool. Beneath that small knob lies a tiny cluster of levers and wheels, switching between winding the mainspring and adjusting the hands depending on how far the crown is pulled. Before this invention, watches required a loose key that could be lost or misplaced. Now the entire mechanism lives inside the case, always within reach of a single turning thumb. 4 years usually pass before a leap day appears, and a perpetual calendar watch accounts for this without anyone touching it. Hidden wheels and levers count months, track shortened Februaries, and skip the extra day only when the calendar truly calls for it. Some perpetual calendars are built to hold this pattern correctly for decades before needing any adjustment at all. It is a small mechanical memory of the sky's arithmetic, carried quietly on a wrist. Gravity pulls differently on a balance wheel depending on which way a watch is oriented, subtly speeding or slowing its rate throughout the day. A tourbillon solves this by placing the entire escapement inside a rotating cage, spinning once every minute or so. As the cage turns, gravity's pull averages out across every angle, canceling its uneven influence. Watching one spin behind glass feels almost hypnotic, a small mechanical dance built purely to outwit the pull of the Earth. Removing the dial and most of the plates lets a skeleton watch reveal its own machinery, gears and springs suspended in open air. Every wheel, bridge, and spring becomes visible from the front, arranged almost like a tiny sculpture caught mid-motion. Craftsman hand bevel the edges of these exposed parts, since nothing stays hidden anymore. What was once a closed engine of hidden ticking becomes, instead, something meant to be looked into, admired for the geometry usually kept out of sight. Adding a stopwatch function to a mechanical watch usually means stacking a separate module atop the base movement, rather than rebuilding it from scratch. Push a button, and an extra set of gears engages, driving a sweeping second hand that measures elapsed intervals. Push again, and it stops, holding the reading until reset. This layered design lets ordinary timekeeping and precise measurement share the same case, working in parallel without ever touching each other's rhythm. Long before electric light reached every home, a minute repeater let its owner hear the time rather than see it, chiming softly in darkness. Tiny hammers strike coiled gongs wound around the movement, sounding out hours, quarter hours, and minutes in distinct tones. The mechanism inside is remarkably intricate, translating the position of the hands into a precise sequence of chimes. Even now, hearing one ring out feels like listening to a small bell tower shrunk down to fit inside a palm. Think of a candle flame low and steady, its light barely moving against the dark. No breeze reaches it here, so it simply glows, undisturbed, burning without hurry toward its own quiet end. You do not need to keep it lit. You do not need to watch it fade. Let your breathing find that same low, steady glow, dimming a little more with every slow exhale, until the light inside you settles and rest arrives on its own. Human eyes alone cannot see the tolerances a fine movement demands, so watchmakers work behind loops and microscopes that magnify each part many times over. Under this magnification, a gear tooth looks like a small mountain range, and a hairspring's coil becomes a visible ribbon of steel. Tweezers guide pieces smaller than a grain of rice into place, movements measured in fractions of a millimeter. This is work done almost entirely by feel, guided by eyes trained to see what ordinary sight would miss. Even a passing truck outside can send faint vibrations through a building, enough to shift a component out of alignment during delicate assembly. Watchmaking benches are often mounted on dampened supports, isolating them from footsteps, traffic, and the low hum of nearby machinery. This stillness lets hands stay steady while placing parts finer than a hair's width. In a factory full of motion, these small islands of calm make the most careful work possible. A focused beam of light can cut metal with more precision than any blade, carving tiny watch components with barely a trace of heat or pressure. Lasers trace patterns fine enough to shape gear teeth, bridges, and decorative engravings in a single pass. Because there is no physical tool touching the metal, wear and distortion nearly disappear from the process. What once took a file and endless patience now happens in seconds, guided by light instead of hand. After machining, metal dust and oil residue cling stubbornly to the teeth of tiny gears, invisible to the eye but harmful to a movement's rhythm. Ultrasonic cleaners solve this by vibrating a cleaning solution at frequencies beyond human hearing, creating countless microscopic bubbles that burst against every surface. These tiny bursts dislodge debris from crevices no brush could ever reach. Parts emerge from the bath looking untouched, cleaned by sound rather than scrubbing. A micrometer is 1/1000th of a millimeter, and within that tiny scale, an entire watch movement must fit together correctly. Pivots, gear teeth, and bridge holes are all measured and cut to tolerances finer than a human hair's width. At this scale, even slight temperature changes in a room can expand metal enough to matter. Precision here is not an ideal to strive toward, but a strict requirement. The whole mechanism depends on to function at all. Robotic arms now assemble many of the world's quartz watch movements, moving with a repetition no human hand could sustain for hours without fatigue. Guided by cameras and programmed paths, they place gears, screws, and tiny springs with unwavering placement, part after part. Factories running through the night owe their pace to these tireless mechanical hands. Somewhere behind a glass wall, a robotic arm is completing a movement while everyone else sleeps. Anti-magnetic alloys shield delicate movements from the invisible fields that surround daily life, from phone speakers to refrigerator magnets. Certain nickel-iron blends bend these fields around the mechanism, rather than letting them pass through. Without this protection, a hairspring could catch and stick, quietly losing its rhythm. Engineers chose these materials so that ordinary life, filled with hidden magnetism, never disturbs the steady beat inside a wrist. Movement testing machines compress years of wear into a matter of days, shaking, winding, and rotating a watch through cycles it would otherwise take decades to endure. Mechanical arms win the crown thousands of times, while sensors record every subtle shift in performance. This accelerated aging reveals weaknesses long before a customer ever notices them. A watch that survives this trial has already lived, in miniature, a lifetime on someone's wrist. Timing machines can detect deviations smaller than a fraction of a second across an entire day, listening to the ticking of a movement the way a physician listens to a heartbeat. Microphones pick up the escapement's beat, translating sound into a visible waveform on a screen. From this pattern, technicians read whether a watch runs fast, slow, or perfectly true. Such fine listening turns an ordinary tick into a story about accuracy. Humidity-controlled rooms keep metal components from expanding or contracting during assembly, holding the air itself as steady as the parts within it. Even a slight rise in moisture can swell certain alloys by amounts too small to see, but large enough to disturb a pivot's fit. Filtered air moves gently through vents, keeping temperature and moisture locked within narrow ranges. In these rooms, the atmosphere becomes part of the tool set, as essential as any file or lathe. Let your jaw loosen just slightly, as though it no longer remembers how to hold anything tight. Let your eyelids grow heavy, resting fully closed, with no effort keeping them that way. Behind your closed eyes, there is only a soft, dim field of nothing in particular, drifting without shape or edge. Let your face rest as it wants to rest, unwatched, unhurried, simply allowed to settle into stillness. X-ray inspection, lets engineers see inside a finished movement without ever opening its case, revealing gear alignment hidden beneath layers of metal. Beams pass through the casing and reveal shadows of internal parts, mapping whether every wheel sits exactly where it should. Misalignment, invisible to the eye, becomes obvious on the resulting image. This quiet form of vision, borrowed from medicine, ensures the smallest components are exactly in their place before a watch ever reaches daylight. Oil viscosity inside a movement is calibrated for the temperatures it will actually meet, since a lubricant too thick in the cold or too thin in the heat can throw off a watch's rhythm. Specialized oils are chosen for specific pivots, gear teeth, and springs, each requiring its own precise thickness. A droplet barely visible to the eye can determine whether a movement runs smoothly for decades. Choosing the right oil is chemistry in service of motion. Watch cases undergo pressure testing to confirm they can withstand the water resistance printed on their dials, submerged in chambers that simulate depths far beyond a swimming pool or rainstorm. Air pressure inside the case is measured before and after, revealing any leak too small to see with the naked eye. A watch that fails this test never leaves the factory floor. Somewhere in that chamber, a seal proves its worth against the weight of imagined ocean. Automated optical inspection scans finished components for flaws no human eye could reliably catch across thousands of parts a day. High-resolution cameras capture magnified images of gear teeth, bridges, and screws, comparing each against a stored, ideal reference. The faintest scratch or misshaped tooth is flagged instantly and set aside. This tireless watching allows factories to hold every piece to the same exacting standard, hour after hour, without ever growing tired of looking. Certification as a chronometer demands weeks, not minutes, of testing. A movement is placed in 5 or 6 positions, dial up, dial down, crown left, crown right, and observed across changing temperatures. Each position reveals how gravity pulls differently on the balance wheel. Only after this long, patient scrutiny does an official body grant the name chronometer, a title earned through sustained proof rather than a single glance. Inside most quartz watches, a tiny crystal vibrates 32,768 times every second. That number is not arbitrary. It is a power of 2, chosen so a simple circuit can halve it again and again until one clean pulse remains each second. The crystal itself is smaller than a grain of rice, yet its rhythm is steady enough to guide the hands of millions of watches without complaint. Electricity, passed through quartz, becomes motion, and motion, passed back through quartz, becomes electricity. This exchange is the piezoelectric effect, discovered in crystals that bend almost invisibly under a charge. A watch battery sends current into the tiny sliver of quartz, and the crystal answers by vibrating at its own natural frequency. The effect asks nothing of the crystal but to be itself, and in being itself, it keeps time. Shaped like a miniature tuning fork, the quartz oscillator vibrates with unusual stability. 2 slender prongs flex toward and away from each other thousands of times a second, a form engineers found by testing many shapes before settling on this one. The fork design resists outside disturbance better than a flat wafer might, holding its frequency steady even as a wrist moves through an ordinary day of small shocks and shifting angles. Once the crystal vibrates, an integrated circuit takes over, counting those 32,768 pulses and dividing them down to exactly 1 tick per second. Rows of transistors smaller than dust perform this division silently, tirelessly, generation after generation. What emerges from this circuit is not the crystal's raw hum, but something calmer, translated into the singular beat that turns a watch's hands forward, second by second. Cold mornings and warm afternoons once meant a quartz watch would drift, however slightly, as temperature changed its crystal's shape. Engineers eventually built compensation directly into the circuit, measuring temperature many times a second and adjusting the timing pulse to match. This refinement, developed through careful trial across decades, lets a modern quartz watch hold its rhythm through winter chill and summer heat alike, indifferent to the weather on a wrist. Let the exhale run a little longer than the breath that came before it. There is no need to count, only to notice the air leaving, unhurried, finding its own length. Each breath in gathers the evening. Each breath out releases whatever the day was carrying. Let the next exhale stretch even further, like a slow tide easing back from the shore. Nothing is required of you now but this simple, repeating give. Etched by light rather than by hand, the crystal blanks that become tuning forks begin as flat wafers of quartz coated in a photographic mask. Ultraviolet light passes through stencil patterns onto the coating, and chemical baths dissolve away everything the light did not protect. What remains is the fork shape, cut with a precision no blade could match. Photolithography, borrowed from the world of computer chips, gives each tiny crystal its exact form. A quartz watch typically loses only a handful of seconds across an entire month, while its mechanical cousin may drift by whole minutes across the same span. This gap, small as it sounds, changed how ordinary people trusted their watches. Where a mechanical movement depends on hundreds of moving parts, staying in delicate balance, quartz relies on a single steady vibration, simpler in its architecture and, in daily life, far more forgiving of time. A single quartz factory can turn out millions of movements in 1 year, each one built from the same handful of components, repeated at extraordinary scale. Conveyor belts carry crystals, circuits, and tiny motors past workers and machines in careful sequence, assembling in seconds what once took a watchmaker hours by hand. This is time made abundant, not by magic, but by repetition, patience, and the quiet arithmetic of manufacturing at scale. Deep within certain factories, silicon dioxide crystals grow not from mountains but from careful chemistry, seeded and coaxed inside pressurized vessels filled with mineral-rich solution. Engineers control temperature and pressure with exacting patience, letting molecules stack themselves into pure lattices over weeks. This synthetic growth means the world no longer waits on nature's slow mineral veins. Instead, laboratories cultivate quartz the way a garden might be tended, though the growing happens inside steel, not soil. Manufacturing scaled sharply once demand for quartz resonators surged through the 1970s. Factories that once produced components by careful hand now installed machinery capable of cutting, shaping, and testing crystals in continuous sequence. Watchmaking, calculators, and early digital devices all pulled from the same growing supply chain. What had been a specialty material became, within a single decade, one of the most reproduced substances in modern industry. Atomic clocks keep time not by gears or crystals, but by listening to atoms themselves. Cesium atoms, when excited by microwave energy, vibrate at a frequency so constant that it becomes a kind of universal metronome. Physicists measure these vibrations rather than count swinging pendulums or ticking springs. In this way, the atom becomes the clockmaker, its inner rhythm untouched by friction, temperature, or wear. The definition is precise, almost beyond imagining. 1 second is 9,192,631,770 vibrations of a cesium-133 atom. This number, agreed upon by international consensus, replaced older definitions tied to the Earth's spin. A single second, once a fraction of a day, became instead a fixed property of matter itself, unchanging wherever it is measured. Just outside Washington, the National Institute of Standards and Technology houses America's primary atomic clock, a device so precise it anchors the nation's official time. Researchers there monitor its output continuously, cross-checking it against sister clocks around the world. The clock itself sits inside a controlled room, shielded from vibration, heat, and stray electromagnetic noise, a quiet sanctuary built entirely for stillness. Optical lattice clocks capture atoms within a structure made of light itself, laser beams crossing to form a grid of tiny wells. Each atom settles into its own cell, held in place without touching any solid surface. Scientists then measure the atom's vibrations using visible light instead of microwaves, achieving a level of precision far beyond older cesium designs. Light, in this sense, becomes both the trap and the measuring tool. Strontium atomic clocks push precision further still, drifting by no more than 1 second across roughly 15 billion years. That span exceeds the current age of the universe itself. Such accuracy allows physicists to detect the subtle influence of gravity on time, since even a slight change in elevation shifts an atom's rhythm. These clocks do not simply tell time, they reveal how gently the universe bends it. Let your body settle, one part after another, into whatever is holding you. Feel your feet grow heavier first, sinking without effort into the mattress beneath them. Let that heaviness climb slowly upward, through your calves, into your knees, spreading like warmth through your thighs. Your hips, your back, your shoulders follow the same downward pull, releasing their hold on the day. Even your hands loosen, fingers curling with nothing left to grip. Let your head rest fully, its whole weight given over to the pillow. Hydrogen maser clocks bring their own gift to timekeeping laboratories, extraordinary steadiness across short stretches of time. While cesium clocks excel at long-term accuracy, hydrogen masers hold remarkably even pace hour to hour, making them ideal companions in national time labs. Technicians often run several side by side, blending their strengths so that no single clock's small imperfection shapes the final signal alone. Fountain clocks send cesium atoms rising gently upward through a microwave cavity, then let gravity draw them back down again. As the atoms rise and fall, microwaves interact with them at their most stable moment near the peak of their arc when they linger longest and drift least. This graceful upward toss, repeated endlessly, gives fountain clocks their name and their remarkable precision, turning something like a fountain's motion into one of humanity's finest measures of time. Rubidium oscillators bring atomic timekeeping into a smaller frame, compact enough to ride aboard satellites and portable enough for field equipment. They lack the extreme precision of cesium or strontium standards, but their size and stability make them ideal companions for machines that must carry accurate time far from any laboratory. Inside each one, rubidium vapor responds to microwaves in a chamber no larger than a matchbox, quietly anchoring signals across the sky. Vibration, isolated rooms buried beneath the earth give atomic clocks the stillness they require to function at their best. Underground placement shields sensitive instruments from traffic, wind, and the faint tremor of footsteps overhead. Springs, dampers, and thick concrete layers absorb what little movement remains. In this hushed subterranean space, engineers create an artificial calm so complete that even a passing truck outside cannot disturb the counting of atoms. Paris holds one of the world's most trusted time reference laboratories, tucked within the historic grounds of its old observatory. Astronomers there once tracked the stars to define the hours. Today, atomic clocks continue that legacy with far greater precision. Domes, built for telescopes, now share their courtyards with instruments that measure vibrations invisible to any eye, linking centuries of timekeeping under one quiet roof. Across continents, atomic clocks quietly check their agreement with one another through satellite links stretched high above the Earth. Signals travel upward, bounce across orbit, and return down to laboratories thousands of kilometers apart. Through this constant comparison, timekeepers ensure that no single clock drifts unnoticed from its distant companions. It is a slow, invisible conversation conducted at the speed of light, keeping the world's clocks in agreement. Leap seconds appear now and then to reconcile the steady pulse of atomic time with the Earth's slightly uneven spin. Our planet's rotation wobbles almost imperceptibly, sometimes slowing, sometimes hurrying, shaped by tides, winds, and the shifting mass within its crust. When the difference grows large enough, timekeepers add a single extra second to civil clocks, a small correction bridging the physics of atoms with the older rhythm of a turning world. The International Bureau of Weights and Measures gathers data from atomic clocks around the globe to calculate a single unified time. Housed near Paris, this quiet institution does not run its own master clock, but instead blends measurements from dozens of national laboratories. Its calculations, published each month, become the invisible thread from which the world's official time is woven. Iterbium is emerging as a candidate for the next generation of atomic clocks, promising precision even beyond strontium's remarkable steadiness. Laboratories trap these atoms in lattices of laser light, coaxing out oscillations so fine they challenge the limits of current measurement tools. It remains an open question how much further such clocks might push the boundaries of what time itself can be measured to. Drift within the finest atomic clocks is now measured in parts per quadrillion, a scale almost impossible to picture. It means these instruments might lose no more than a single second across tens of millions of years. Such numbers stretch far beyond ordinary experience, yet they represent something real, a rhythm so steady that entire human lifetimes pass within a single tick's margin of error. Somewhere beyond these walls, a low hum moves through the building, rising faintly, then fading again. It might be wind against a window, or a house settling into the cool of night. There is no need to trace its source. Let it pass through you, the way it passes through the room, arriving softly, drifting away, leaving nothing behind but a little more stillness than before. High above the Earth, GPA satellites carry their own onboard atomic clocks, each one ticking with the steadiness required for precise navigation. These orbiting instruments measure time so finely that even the tiny effects of gravity and velocity described by relativity must be corrected for their signals to remain accurate. A phone in a pocket, a ship at sea, a plane crossing an ocean, all quietly depend on clocks circling far overhead. Atomic clock networks span continents, forming the backbone of what the world now calls coordinated universal time. Signals travel between laboratories in Boulder, Braunschweig, and Tsukuba, comparing their ticks against one another. No one clock holds the truth alone. An average of many becomes the standard. This shared rhythm, stitched together across oceans, lets a satellite and a smartphone agree on the same fraction of a second. Cooling a clock's cesium atoms closer to absolute zero makes its frequency steadier still. Cryogenic chambers slow the atom's motion, dampening the random jitters that blur a resonance. Engineers wrap the resonator in layers of insulation and refrigerant, easing out noise born of heat. The colder the atoms rest, the more faithfully they mark the passing second, a steadiness measured in fractions no ordinary thermometer could show. Chip-scale atomic clocks now fit inside portable military devices, no larger than a matchbook. Inside each tiny package, a vapor cell holds cesium atoms warmed by a laser rather than cooled by machinery. Soldiers carrying these devices gain navigation and communication timing even where satellite signals cannot reach. What once filled a laboratory room now rests in the palm of a hand. Time laboratories keep several atomic clocks running side by side, never trusting one instrument alone. If one clock drifts, the others outvote it, and the discrepancy is caught before it spreads far. Redundancy, built into rows of humming cesium and rubidium devices, protects the fragile agreement that lets nations share the same second. Precision, it turns out, depends on company as much as accuracy. Coordinated Universal Time serves as the world's master reference, the figure every other clock checks itself against. Airlines, banks, and broadcasters all set their instruments to this shared standard, even as their local hours differ by name. Beneath every stated hour, whatever the country, the same underlying second ticks along. It is less a place than an agreement, invisible and universally trusted. This master time blends the steadiness of atomic clocks with the older rhythm of Earth's own turning. Pure atomic time would drift slowly away from the length of an actual day, since the planet's spin is not perfectly even. To keep the two aligned, adjustments are occasionally folded in, honoring both the machine's exactness and the world's ancient turning beneath it. The Greenwich Meridian once anchored global timekeeping, a line drawn through an observatory garden in London. Ships set their chronometers by its noon, and nations gradually agreed to measure longitude and hours outward from that spot. A brass strip in the courtyard still marks 0 degrees, where east meets west on every map. From that modest stretch of grass, the world learned to count its hours together. Time zones divide the world into 24 standardized offsets from coordinated universal time, each an hour's width wrapped around the globe. Before this system, every town kept its own solar noon, making train schedules a puzzle of local variations. Railways, more than any government, pushed the world toward these tidy hourly bands. Today, a traveler crossing a border can predict, almost to the minute, how the clock on the wall will change. Earth's rotation is tracked by an organization known as the International Earth Rotation and Reference System Service, watching the planet spin for the smallest irregularities. Its researchers monitor how the axis wobbles and how the length of a day shifts by fractions of a millisecond over months. These measurements feed directly into decisions about leap seconds, keeping human clocks aligned with a planet that never turns quite the same way twice. Let a warmth begin somewhere near your feet, spreading upward the way morning light moves across a floor. Feel it reach your ankles, then settle into your knees, loosening whatever the day left tightened there. Let it rise through your chest, unhurried, filling the space behind your ribs like a held breath finally released. Let it reach your shoulders, your jaw, the small muscles behind your eyes, until every part of you rests at the same warm, unmeasured temperature. There is only this slow spreading, and the dark, and the rest that follows. Clocks shift twice a year across many countries, a practice known as daylight saving time. Regions push their hours forward in spring and backward in autumn, chasing a little more sunlight into the evening. Farmers once resisted the idea. Factory owners championed it. Whole nations still argue over whether the extra hour of daylight is worth the disruption to sleep and habit. A small seasonal ritual layered on top of the atomic precision beneath it. An organization called the Bureau International des Poids et Mesures gathers measurements from atomic clocks around the world and publishes the official reckoning of time itself. Housed near Paris, it compares readings from dozens of laboratories each month, averaging their small disagreements into a single trusted figure. No single clock is declared correct. The truth is built from consensus, a quiet negotiation among machines that never meet in person. National laboratories broadcast their most accurate signals outward, offering industry a shared heartbeat to build upon. Factories, banks, and broadcasters tune receivers to these transmissions, letting distant atoms set the rhythm of local machinery. A power plant in one country and a stock exchange in another may draw their timing from the very same pulse, arriving through the air rather than through any wire. Legal time, in most nations, is not a matter of physics at all, but a matter of law. Governments choose which offset applies within their borders, sometimes for convenience, sometimes for politics, sometimes simply for tradition. A country can move its clocks by decree, unmoored from any celestial requirement. The atoms keep their perfect count regardless. It is the paperwork of nations that decides what hour we call it. The doomsday clock keeps no actual time. Created by a group of scientists after the Second World War, its hands are moved by committee each year to represent how close humanity seems to catastrophe, not how many minutes remain until noon. It has no gears, no battery, no atoms vibrating inside it. It is a metaphor built to look like a clock, borrowing the shape of urgency without any of the mechanism. Railways once demanded something no town had ever needed before: a single shared hour across hundreds of miles of track. Before trains, each village kept its own solar noon, and a schedule written in one town's time meant little in the next. Collisions and missed connections followed until railway companies imposed standardized time along their lines, quietly rewriting how entire regions agreed to measure their days. A telephone service once let anyone in the world dial a number and hear the precise time spoken aloud. Known as the speaking clock, it offered ordinary callers access to laboratory-grade accuracy, long before quartz watches were common. A recorded voice, calm and unhurried, read out the hour, minute, and second, again and again, day and night, for anyone willing to lift a receiver and listen. Towers once rose above cities for no purpose but broadcasting time. Radio pulses, sent out at fixed intervals, let distant clocks correct themselves automatically, keeping factories and railways aligned without anyone climbing a ladder to adjust a dial. These towers hummed through storms and clear nights alike, sending their invisible ticks across valleys and rooftops to every receiver tuned to listen. Somewhere in Colorado, a station called WWB sends time signals steadily across an entire continent. Its broadcasts reach millions of clocks and watches without their owners ever noticing, correcting drift while people sleep. The signal travels low and slow, wrapping around mountains and plains, carrying nothing but the patient certainty of a number ticking upward second by second, mile after mile. Across the internet, a protocol called Network Time Protocol keeps distant computers agreeing on the hour. Servers exchange tiny packets, measuring the delay of their own questions to correct for the time a message spends traveling. Billions of machines, from laptops to satellites, quietly borrow their sense of now from this constant, invisible negotiation, threading a single shared moment through cables laid across oceans. Let your attention rest on something small and slow, dust drifting through a beam of late light, turning without hurry, going nowhere in particular. Each speck rises and falls on air too faint to feel. Your breath can move the same way now, rising, falling, asking nothing of you. There is no task waiting on the other side of this moment, just the dust, the light, and the long, easy dark behind your eyes. Financial markets now require timestamps accurate to millionths of a second. When a trade executes, its exact moment must be provable down to the microsecond, so that disputes can be settled and fairness verified. Trading floors that once ran on wall clocks now synchronize to atomic time distributed through fiber lines. In these systems, a delay barely longer than a blink can separate one trader's advantage from another's loss. Telecommunications networks depend on synchronized clocks to route every call and message correctly. Without shared timing, data packets would arrive out of order, calls would drop, and towers would lose track of which signal belongs to which conversation. Engineers describe this hidden timing layer as the network's heartbeat, steady and continuous beneath every ordinary exchange of words passing invisibly between phones. Power grids rely on precise timing to keep supply and demand in balance. Generators across a country must spin in step with one another, their alternating currents lock to the same rhythm, down to fractions of a cycle. If that rhythm drifts even slightly, transformers strain and blackouts can follow. Atomic clocks now anchor this rhythm, letting distant power stations breathe in the same slow electrical tempo. Global navigation satellite systems depend entirely on synchronized atomic time. Each satellite carries its own precise clock, broadcasting a signal stamped with the exact moment it was sent. A receiver on the ground compares these tiny time differences to calculate its position, turning fractions of a second into meters of certainty. The whole system, quite remarkably, is really a clock network wearing the disguise of a map. Stock exchanges are legally required to timestamp trades to atomic clock precision. Regulators mandate this so that when thousands of transactions happen within the same second, their true order can still be reconstructed. Exchanges lease atomic time feeds the way factories once leased electricity, treating precision itself as infrastructure. A trade's timestamp has become as important as its price. Shortwave radio once carried time signals across continents, bouncing off the upper atmosphere to reach places wires could not. Ships at sea, remote outposts, and traveling explorers tuned their receivers to these faint broadcasts, setting their instruments by a rhythm sent from laboratories thousands of miles away. The signal arrived thin and crackling, yet reliable enough to guide ships home by starlight and static alike. Submarine cables now carry synchronized timing data between nations, threading along ocean floors where light and pressure rarely reach. These cables, originally built for voice and data, now double as timekeepers, letting laboratories on opposite continents compare their atomic clocks to trillionths of a second. Beneath the waves, in total darkness, time itself travels quietly as pulses of light, through glass no thicker than a hair. GPA's receivers extract precise time as a byproduct of positioning signals, almost as an afterthought to their main purpose. A device seeking only to know where it stands also learns, without asking, exactly when it stands there. This hidden gift of time now powers countless systems that never needed a map at all, only the clock riding quietly inside the signal. Cell towers synchronize using GPS-derived time signals, aligning their transmissions so that calls and data pass smoothly from one tower's coverage into the next. Without this shared timing, a moving phone would lose its connection at every boundary, the conversation breaking apart mid-sentence. Instead, towers hand off calls in perfect step, borrowing their timing from satellites overhead that most callers will never think to notice. Vast halls of humming servers hold clocks that answer to atomic time. Each transaction, message, and search request receives a timestamp drawn from a cesium reference kept far away, often in a separate room, shielded from vibration and heat. This shared reference lets a bank in one country and a marketplace in another agree, to the microsecond, on when an exchange took place. The number on a receipt feels ordinary, yet behind it hums an atom's steady pulse. Notice the muscles framing your eyes and let them lose their hold. The jaw follows, unclenching by its own weight, lips parting just slightly. Behind closed lids, the dark deepens into something formless, without edges to follow. There is only the warmth of your own breath returning to your face, again and again, asking for nothing more. Devices everywhere send a small request outward, asking a distant server what time it is. Laptops, routers, security cameras, and thermostats all check in this way, often without anyone noticing the exchange. The reply travels back in a fraction of a second, correcting drift before it can grow into disagreement. Across billions of machines, this constant asking and answering keeps the digital world moving in step. Threads of glass, laid specifically for timing, connect national laboratories across borders. Metrology institutes exchange their most precise clock readings through fiber links built to carry almost no delay at all. A pulse leaves a laboratory in one country and arrives in another before the length of a heartbeat passes. Through these dedicated strands, the definition of a second stays consistent from continent to continent. Television networks lean on a single master clock to keep every camera and broadcast tower in step. Without this shared reference, a live picture from one studio might drift out of rhythm with its sound, or with a feed from another city entirely. Engineers monitor this master signal constantly, adjusting for the smallest deviations before viewers ever notice a flicker. The evening news, in this sense, is also a small feat of timing. Emergency dispatchers rely on synchronized clocks to coordinate every call for help. When a fire truck, ambulance, and police unit respond to the same address, their radios and records must agree on timing down to the second. This shared clock lets responders reconstruct exactly what happened, and when, long after the moment has passed. A dispatcher's log, precise to fractions of a minute, becomes a steady form of care. High above the clouds, aircraft cross paths, guided partly by clocks no pilot ever sees. Air traffic control systems depend on synchronized time to track each plane's position and predict its path safely alongside dozens of others. A discrepancy of even a fraction of a second could blur the picture controllers rely on to keep flights apart. Instead, precise timing keeps the skies in visible traffic moving in patient, ordered lanes. A smartphone rarely needs to be told the correct time by its owner anymore. In the background, it checks in with network signals, adjusting its display without ever asking for permission. Crossing a time zone, boarding a plane, or simply waking after months in a drawer, the clock corrects itself within moments. This small automation spares millions of people a task they no longer remember having to do. Bluetooth and Wi-Fi connections require timing so precise it is measured in millionths of a second. Two devices exchanging a wireless signal must agree almost exactly on when each packet of data begins and ends. Without this tight coordination, headphones would lag behind video, and wireless networks would tangle their own transmissions. Beneath the convenience of a wireless connection lies an unseen negotiation over time itself. Across a network of scattered computers, a blockchain ledger keeps its own record of time. Every transaction added to the chain carries a timestamp agreed upon by distributed consensus, with no single clock in charge. Thousands of machines, often on different continents, must align closely enough to accept the same sequence of events. In this way, trust in the ledger depends as much on shared timing as on the transactions themselves. In laboratories built to detect the faintest ripples in spacetime, two detectors separated by thousands of kilometers must agree on time to within a billionth of a second. Gravitational wave observatories compare their readings using atomic clock references, searching for the same faint signal arriving moments apart. Without this nanosecond precision, a passing tremor from deep space would look like noise rather than discovery. Physics, at its most delicate, still depends on knowing exactly when. A self-driving car reads the world through cameras, radar, and LiDAR, each system reporting on its own clock. To merge these streams into a single coherent picture, the vehicle's computer must align every sensor reading to a common time base measured in fractions of a millisecond. A poorly timed frame could place an obstacle where it no longer is. Beneath the calm glide of an autonomous vehicle runs a constant, invisible act of temporal stitching. Let your breath find its own rhythm now, without any need to guide it. In through the nose, and then a long, unhurried release, longer than the breath before it. Each exhale can travel a little further than the last, spreading warmth down through the shoulders, the arms, the open palms. There is no pace to keep, only the next easy breath, arriving whenever it arrives and leaving just as slowly. Switzerland, a country smaller than many single country's provinces, ships timepieces worth billions of dollars abroad each year. Its watch exports outweigh many industries, many times its size, carrying a reputation built across centuries of small workshops. Every strap, dial, and case that leaves its borders carries a story of mountain valleys and generations of patient hands. A nation's economy, in part, keeps running on wrists around the world. A luxury watch factory sells more than a mechanism for tracking hours. Its advertisements linger on hand, beveled edges, the grain of a dial, the weight of solid gold against skin. Craftsmanship becomes the story being told, often as important as the seconds the watch actually keeps. People buy the patience of the artisan as much as the accuracy of the escapement inside. A trader in Tokyo and a buyer in New York can settle a deal within seconds, their agreement anchored by clocks that read the same instant despite the ocean and hours between them. Global commerce depends on this alignment, letting markets, shipments, and contracts move without confusion over when something truly happened. Trade across time zones works only because time itself has been made to agree. In small towns, scattered through mountain valleys, watch factories have employed the same families for generations. A grandmother once assembled the very gear train her granddaughter now finishes by hand. These workshops carry knowledge that resists easy replacement, passed through apprenticeship rather than manuals. In such places, timekeeping is also a family inheritance, measured not in hours but in decades of shared skill. Before factories learned to manufacture time, people measured their days by the sun's arc, the length of shadows, the turning of seasons. Once clocks multiplied, time became something owned, sold, and standardized, detached from the sky above. Human life reorganized itself around dials and schedules rather than daylight and dark. The rhythm of nature gave way, slowly, to the rhythm of the machine. In 1884, delegates gathered in Washington for the International Meridian Conference, tasked with dividing the globe into orderly bands of time. They settled on Greenwich as the reference point from which every other hour would be measured. What had once been a patchwork of local noon became a single, agreed structure spanning continents. A room full of diplomats effectively redrew the shape of every day on Earth. A smartphone in nearly every pocket now performs the job that once required an entire factory devoted to clocks. It receives its time from satellites and networks, correcting itself endlessly without human help. Many standalone clock manufacturers have quietly closed their doors, their function absorbed into a device that fits in a palm. The great machinery of time production has, for most of us, shrunk into glass and circuitry. In certain workshops tucked between old stone walls, artisans still finish a single movement across many months. Each bridge is beveled by hand, each screwhead polished, until it mirrors light like a small black star. No machine rushes this labor, and no deadline hurries the file across brass. The maker simply keeps returning, day after day, until the metal agrees to be perfect. Inside glass cases in old museums, the tools of early clockmakers rest on velvet, as though still warm from use. Hand files, tiny lathes, and worn wooden mallets sit beside sketches of gears drawn by candlelight centuries ago. Curators treat these objects not as scrap metal, but as memory made solid. What once shaped hours now simply waits, admired as a record of patient human hands. Across brass and quartz, cesium and code, the drive toward finer and finer time reveals something quietly human, a wish to hold the ungraspable, to press order onto hours that would otherwise simply pass. Every gear cut, every atom counted, has been an attempt to keep the world from slipping away too quickly. And now, as your own hours draw softly toward rest, that vast machinery of clocks and satellites keeps its watch, so you don't have to. Let it. Sleep now, unmeasured, and let the world keep the time for you. Good night.